Well, welcome out here to physics land. It's actually a sunny day for me, so I'm going to spend some time outside working on my tan after this is over with. Next time you see me, I'll have some nice tan, maybe forehead and cheeks. Of course, not anything in the eye or in the mouth area, right? You know what I mean? Okay, so this one is on center mass. My name is John Frensley. I teach Prosper High School about 30 miles north of downtown Dallas. This one is going to be pretty good for both C mechanics and P1. P1 up to about 2/3 of the way. So I'll tell you P1 kids when you can tune out, because it's going to turn into some mathy stuff that's really only for physics C. Just a plug once again for my Facebook page. If you search up my name, Frensley Physics Facebook, those three terms, Frensley Physics Facebook on Google, then the first link will be to a Facebook page. You do not have to have a Facebook account. You don't have to pay any money, but scroll down to posts and you'll see one question for each of the 4 levels of AP Physics, 1, 2, C Mechanics, and C EMAG. Every day, solutions on the next day. And watch out, because some of the mechanics questions also work for P1 and vice versa. Some of the P2 questions go to C EMAG or vice versa, and they are noted if they have that overlap. All right, let's do a warm-up. We're going to talk about center of mass today, and this is just a really simple one right here. This is a classic conceptual question, so if you see it before, you already know the answer. If you haven't seen it before, then you get a chance to see it now. Remember, all the questions I'm asking you, I'm trying to make it like the format of this exam, where it's going to be pretty much text only. So if you want to have the pencil and a piece of paper you can write on, you can work out the little problems, write out answers, or a little window open for your word processor to practice this would be good. So we got a hammer, it bounces on that X, right? So if you cut the hammer in half on the X, which piece, notice I didn't say half, which piece would be greater mass, or would they both have the same mass? I'm gonna give you 2 minutes to think about it. On your mark, get set, go. That's enough of that, right? We'll answer this here in a little bit, but let's just go over what we're going to talk about today. We're going to figure out why the center mass, which is a special point for a system or an object, is so important. We're going to calculate where the center mass of an object or system is, and we're going to figure out how the center mass changes its motion, right? So first and third bullet points we'll do first, because that's more for C and P1. Middle one is more for C, so it's going to be at the end. I'll warn you when the P1 kids can tune out, like I said. Okay, so here's what you need to know. Every object or system has a special location called its center mass. And if you want to imagine like what it means like, imagine you put the object or system on a massless light plank or board or something. The center mass is where the fulcrum could be set to balance it, right? So every single point every single object has a center of mass. For example, in a human, it's kind of up here in kind of the chest area, kind of in the sternum type thing. So if you could come up with a board that's very, very light compared to me and lay me out on it, you could put the fulcrum right underneath that point of my body, and I would mostly balance, right? I would balance the best I could, right? It's a little difficult for people like me to balance because I'm not very good at it, right? Now, the center mass of the hammer is closer to the metal end because that end is heavier. So if you have a heavier part, then that part is going to be where the center mass is closer to. One of the things I found out very early when I was a dad was I put my baby onto the changing table and she liked to kick. So she would gradually kick herself off. So I'm trying to get the diaper ready and everything cleaned up and stuff. And she would gradually kick herself over the edge on the head side, right? Well, she got to the point where about her neck was over, and I'm like, she's not going to kick herself over. And then she almost goes over into the trash can that's there, and I grab her, and of course I don't tell my wife this, and she doesn't watch these videos, so she'll never know, but that's when I realized that a baby has a center of mass. It's way closer up here than a normal sized human, right? You can see here in this right diagram sort of how the center mass of the human body changes its location based on whether your arms are down or up or sideways. Please note that the center mass does not actually have to be within the physical object itself. So for example, a boomerang would have the center mass out here somewhere, which is not physically inside the wood of the boomerang. You can see that here with this human, right? So center mass human's kind of within the chest, which is not what this diagram seems to show very well, but it's closer to your heavy head. Your head should be heavy, right? There's a big brain in it, right? And the feet are not so much, right? And you can change the position of your center mass by redistributing the atoms in your body to a different shape, sort of thing, right? Okay, so what's important? What else is important about the center mass? Well, if you take like a hammer and you throw it, don't actually do this at home, but if you throw a hammer like the Hammer Brothers from Super Mario Brothers, then the hammer will spin, but it's the center of mass that the hammer spins around, and that center of mass is what makes the parabola in the projectile motion. So it's the center of mass that actually makes the parabola when an object is in a projectile motion type situation, right? Okay, here we see Simone right here, and she's doing her nifty gymnastics routine. I found a nice animated GIF of that on the internet. I did not write a program to do that. And you can see that her center of mass, she spins around her center of mass as soon as she stops touching the balance beam and right before she reaches the ground. So when only gravity is acting on an object, then the center of mass is what follows the parabola, right? And so there you go. And she tucks in and she spins around really fast. It's a rotational concept we'll learn about next week. So we got this guy, he's going to drop a spring. And this is a really cool experiment I encourage you to try. I give my students bonus points for doing this, where they film in slow motion a slinky and they hold a basketball right next to the center of the slinky and they let both of them go, maybe in a stairwell in your school. Okay, get permission from somebody at your school before you try this. But then what the slinky will do is it will compress and the basketball will fall. And once the slinky's compressed, the basketball and slinky will both fall together, just like that experiment that your teacher taught you with Galileo and the heavy and light object fall together. So if I could use my mouse to mimic the basketball here, I'll let the animation reset. So let's let the mouse cursor be the basketball here. So when he lets go, let's say I let go of the basketball, and the basketball will be right next to the center mass of the slinky, and they both will fall together. Once the slinky's compressed, they'll be side by side. So once he lets go of the slinky, it's the slinky center of mass that has an acceleration 9.8 meters seconds squared. Well, the bottom still isn't accelerating yet. So the top actually accelerates faster than 9.8. So that the averages out for the center mass 9.8 meters per second squared. So if the only force acting on an object or system is gravity, the center mass is the thing that's actually in free fall. All right. Every system has a center mass. So if you were to set the objects on a board, then the center mass where they would balance, where the fulcrum could be set right. So the Earth-Moon system has a center mass, which is somewhere in the Earth's interior. So if I could put the Earth and the Moon onto a long plank and somehow put a fulcrum there with some other gravity, maybe the sun or something, then the center mass would be so close to the Earth's center that it's actually about a third of the way into the Earth's interior from the surface, right? Now, So what does that mean for the hammer? Well, it turns out that if you cut the hammer in half, then the left side piece was actually going to be the heavier one. So if this is what you answered, you should have said that the left side piece is heavier because it's closer to the center mass. The right side piece is lighter because it's farther. So the center mass is closer to the heavier object, right? So you might have learned this from either your physics teacher, your junior high teacher, your parents, or PBS or somewhere. You might have learned that the Earth stands still and the moon circles the Earth in a circular orbit. Well, that's not entirely the truth. The truth is that it looks more like this, where the center of mass stands still and the Earth and the moon are both on opposite sides of the center of mass at any given time, with the Earth's center closer to the center mass, the moon's center farther to the center mass, the moon is lighter, right? Now, if you would like to mimic this, here's another thing that I've done, let's say with my 4-year-old, is pick up my 4-year-old by her arms and swing her around. Now, of course, when I swing her around, it kind of looks like this, where the moon is like my 4-year-old, she makes a big circle, but my center mass makes a small circle on the opposite side of our mutual center of mass. Our mutual center of mass is what stands still. And of course, she loves that because it's like being on a roller coaster ride. She's too young for it at the moment. Now consider Pluto and however you pronounce the name of it, Sharon, Karen. It's Karen, right? Okay, have we heard about the whole thing with the Karens? What is that about anyway? So so apparently you're supposed to pronounce Pluto's moon Karen. Just make whatever joke you want to make right now. Anyway, it turns out that Pluto is so light compared to its moon that their mutual center mass is outside of the interior of Pluto or its moon, whose name I don't know how to pronounce, right? And so so they both orbit their kind of mutual center mass, which in space is called a barycenter. And that's not going to show up on the AP exam, but it's worth knowing. B-A-R-Y center, barycenter, right? All good. So this is what's actually happening between the Earth and the moon. Now, I did not put the center of mass exactly within the Earth, but I made it a little bit outside the Earth to embellish what's going on. But this is what's actually happening. So about 12 times a year, the Earth-Moon system completes an orbit around its mutual center mass, and the mutual center mass is what actually makes the orbit. I guess I did not set the animation to repeat automatically. That's sadness. But it's actually the Earth-Moon center mass that makes the circle around the sun. And technically, the sun itself is actually slightly displaced from the center mass. So when the Earth and moon are on top of the circle, the sun is slightly below the circle, orbiting their mutual center mass. Just the sun is so heavy that the center mass is so close to the center of the sun. It's like a couple of miles off from the center of the sun. So we just put it at the center of the sun. It's so huge anyway, right? Okay, so what if you have a two-object system? So P1 students need to be able to calculate where the center mass is of a two-object system. So let's say your two objects are M1 and M2. M1 is distance 1 away from the center mass. M2 is distance 2 from the center mass. So they're just an inverse proportion, right? So M1 times its distance from the center mass equals M2 times its distance from the center mass. So let's say that I have, I don't know, let's say that M1 is 8 and its distance to the center mass is 3. Then if M2 was 6, its distance to center mass would be 4, because 8 mass times 3 distance would equal 6 mass times 4 distance. And it works in any units. It could be grams, kilograms, miles, meters, kilometers, astronomical units, doesn't matter, as long as the two mass units are the same, the two distance units are the same. So don't freak out about the fact that this problem is going to be in centimeters, because it still works. It's got a 2 kilogram object that's attached to one end of a meter stick. The 3 kilogram object is attached to the other end of the meter stick. So I just want to know which of these centimeter marks is where the center mass is. So really all you're asking is, where is it that the center mass has to be so that M1 distance 1 equals M2 distance 2. So I'm going to give you, let's say, I don't know, 2 minutes. On your mark, get set, 2 minutes. I'll show you the official mathy way in a moment, but instead I'm going to do it the unofficial process of elimination way. First, I know that the center mass is somewhere between 50 and 100 because it's got to be closer to the heavier mass. So I'm just going to try each number, each position, and test and say, could this be the center mass? For example, could 90 be the center mass? 2 times 90, 3 times 10. Those aren't the same numbers, so no. 80, could 80 be the center mass? 2 times 80, that's 160. 3 times 20, that's 60. No, that's not the same number. Okay, let's try 70. Okay, 2 times 70, it's 140. 3 times 30 is 90. No, that's not the same number. How about 60? Could 60 be the center mass? 2 times 60, that's 120. 3 times 40, it's also 120. I think 60 is where the center mass is located. 2 times 60, m times x, equals 3 times 40, also m times x. Or you could do it the official mathy way. You could say the distance to the center mass from the left is x and y from the right. So wherever it is, 2 to the center mass is x, 3 of the center mass is y. So 2x, mass times distance equals mass times distance. Also, the two lengths have to add up to 100. So then I just do a little bit of substitution. I distribute, I get my like terms together, and I divide an x. The distance from the left to the center mass is 60, right? So x is the distance from the left to the center mass. Y is the distance from the right to the center mass, which will also be 40, right? So that's where the center mass is located. Isn't that lovely? Yay. Okay, here's some more stuff you need to know, and especially in Physics C and in P1. If an object is moving, or any object in the system is moving, then the system's center mass could, doesn't have to, could be moving. So if any objects in the system are moving, the center mass could be moving. The velocity is determined by the net momentum of the system. I know that the screen says total, but I'm trying to get in the habit of saying the word total only when I'm adding up positive numbers, and net when I'm adding up numbers that could be negative. Momentum could be negative. Momentum is negative if you're moving to the left or down, right? So the velocity of the center mass is determined by the net momentum on the system. Here's how I remember it. I remember momentum is mass times velocity, but that's for one object only. One object's momentum is that one object's mass times that one object's velocity. On the other hand, for center mass, you take the net momentum of an entire system and you take the entire system's mass, then the V is the velocity of the center mass. So it's the same equation again. This is not a new equation. P equals mv for an individual object, P net for a whole system, m total, mass can only be positive total, m total for a whole system, V of the center mass. P equals mv. P equals mv for an individual, P net of a system equals m of the whole system, V of the center mass of the system. Same equation. So let's have a look at what's going on here. So here's an example. We got the red car has twice the mass of the blue car. So do you notice, look carefully, that the center mass is twice as far from the blue car as it is from the red car, right? So let's see it again. Is it going to repeat? Grr, it's not going to repeat. Why does this animation hate me? Okay, so what you'll see again is you'll see that the center mass is always twice as far from the blue car as it is from the red car, okay? All right, now I'm gonna do something really risky here. I'm gonna start my animation over again. It might fix a lot of the problems I'm having here. Okay, so now I'm gonna find the center mass just using momentum principles. So here's what I'm gonna say. I'm gonna say the momentum before, we got 1 kilogram going 6 meters per second. Watch the animation, you'll see the 1 kilogram going 6 meters per second, and the 2 kilogram is going 0 meters per second. Okay, it's not refreshing my animation. That makes me a sad panda. Okay, so look right here. The 1 kilogram is going 6 meters per second. The 2 kilograms going 0. So then that's 6 kilogram meters per second worth of momentum. So I'm going to say the net momentum is 6 kilogram meters per second. The total mass of the two carts is 3 kilograms. So the velocity of center mass is 2 meters per second, which is what you saw in the animation. So let's see one more time. Here's the center mass going 2 meters per second. But did you notice the center mass still goes 2 meters per second the whole time? Even though the 1 kilogram and the 2 kilogram change their velocity in the collision, the center mass keeps the same speed. This is because momentum is conserved in the collision. Any collision that conserves momentum, the center mass keeps the same velocity. So conserved momentum, the net momentum is constant. So since the momentum before and after is the same, the velocity of the center mass is the same before and after. Even though the two carts changed their motion, the center mass did not change its motion before and after. So how do you change the motion of the center mass? Well, you have to do the same thing as changing a momentum. And that is if you have a force on the system that is both unbalanced and external. Unbalanced. There's no other force canceling it out on any other object in the system. external. The thing doing the forcing is not part of the system. In the animation you just saw, there were no unbalanced external forces. There were unbalanced forces, but none of them were external, and there were external forces, but the external forces balanced and the unbalanced forces were internal to the system. So if you want to accelerate your center of mass, you need there to be a net force on the system. It can't be an internal force, because when you add up all the force on the system, the internal forces will cancel out. And it can't be a balanced force, because then when you add up all the balanced forces, you'll get zero anyway. But if you get a net external force that's unbalanced on your system, then you set that equal to the total system's mass. You can solve for the acceleration of the center of mass, just like Newton's second law. So we're not really teaching anything new today. This is all old. This is P equals mv, but for a whole system and the velocity of the center mass. Force net equals ma, but all the forces on the system and the total mass of the system and the acceleration of the system's center of mass, right? So what are the forces acting on this system? Well, we've got weight, which is an external force. It comes from the Earth. That's not part of the red-blue system, but that's balanced by the normal force, which is external. It comes from the ground, not part of the red-blue system. But weight and normal cancel. Same on the blue. Weight from the Earth, not part of the system. Normal from the ground, not part of the system, cancels out. So they are not unbalanced external forces. They're external forces. They are not unbalanced. On the other hand, the blue cart pushes the red cart using the spring. Blue and red are both in the system. That's an internal force. Red pushes back on blue with the same force in the opposite direction at the same time. Newton's third law. That's an internal force, because red and blue are part of the system. Therefore, there are no forces that are both unbalanced and external at the same time. So because we have no forces that are both unbalanced and external, then we cannot change the motion of the center mass. There are no unbalanced external forces, so the center mass cannot change its motion. All right, I'm going to let you see it one more time here. I'm going to let you see it one more time. So here's the animation. I'm sorry that it won't repeat. That makes me sad. I'd really like for the animation to repeat, but you can see how the center mass keeps its 2 meters per second velocity the entire time. Now, this is the two carts, and they're sprung together with the spring again, but now we do have an external force. It's the 2.4 newtons that you see here. So now we do have an external force, right? We still have normal and weight, and the two spring forces, normal and weight, are external and cancel. The two spring forces are internal, so they cancel out when we look at the whole system, right? So the pink, oh, good, this one actually repeats. So the pink arrows represent the internal spring force on both carts, so that's internal. So you get a right force on the red, on the blue, and a left force on the red. Those cancel out when you look at the system as a whole. All right. Now, the internal spring force cancels out when we look at the system as a whole, right? However, when we have and notice, look very carefully, that if you look at one object, like if you look just at the blue object, if you just look at the blue cart, it has a lot of acceleration when its pink force is high. So notice what I did is I changed the system on you. Looking only at the blue as a system, the spring force is now an external force, and the blue cart center mass changes motion. Looking only at the red has a lot of acceleration, except when his backwards force is big. Looking only at the red, the external forces are the green 2.4 newtons and the pink spring force. But looking at the two carts as a system, the spring force is internal and the green applied force is external. So the external force is 2.4 newtons. The total mass is 3 kilograms. So the center mass is gaining 0.8 meters per second every second. The center mass accelerating 0.8 meters per second every second. So notice, even as the two carts do this wiggly woo with the spring, the center mass has a constant acceleration because there's a constant net force on the system, net external force. The spring doesn't matter to the center mass. The spring matters to just the blue. The spring matters to just the red, but the spring doesn't matter to the system as a whole. Only the green force matters to the system as a whole. Okay, so we talked about that. The external force 2.4, the total mass is 3. So the center mass acceleration is 0.8. Even as the carts wiggle, the center mass has a constant force, so it has a constant acceleration. Okay, so here's what's going to happen. What you're about to see is an animation where there's going to be an explosion between these red and blue boxes. These are not the carts anymore. These are boxes. They have friction. So when the explosion pushes the two boxes apart, and they're both going to have the same coefficient of kinetic friction, even though they have different masses, you're going to watch the center mass speed up to the left, then slow down to the left. That's the graph right here. Speed up to the left, slow down to the left. So here's the question. Why does the velocity of the center mass change the way that it does? So this is going to be a good text answer. This could be a paragraph length response, and it could be on P1 or C. So we're all going to work together on this with our little word processor. You're going to explain to me, why is it that once the explosion happens, the center mass speeds up to the left, then later slows down to the left? And you have to explain it without the animation, because I ain't going to animate it for you on the actual AP exam. So here's some time to figure it out. On your mark, get set, go. All right, so let's actually look what the animation looks like. So there's the explosion and the carts are shot apart, but friction brings them to a rest. And if you watch, because you get, oh, please, okay, it loops, good job. All right, you'll watch as you see the center mass increasing in leftward velocity, then decreasing in leftward velocity. So what on earth is happening, right? Well, watch carefully. When both boxes slide, since they have the same mu, the 2 kilogram has greater friction, greater leftward friction. So look carefully. Here it is. You can see that gray left arrow F on the 2 is better than the gray right arrow F on the the gray left arrow F on the red is better than the right arrow F on the blue. So I'm thinking this: normal and weight cancel when we look at the whole system, but the left arrow F on the red is better than the right arrow F on the blue, both of which are external forces that don't balance. So if the left force is better than the right force, that speeds up your leftward motion of your center of mass. So while both boxes slide, the net force on the system is the leftward friction, which is better. So the center mass gains leftward velocity. So what causes it to lose its leftward velocity? Look at the fact that the red box quits moving first. Why does the red box quit moving first? Because when two objects are exploded apart, the heavier object has less velocity coming out of that explosion. So the 2 kilogram box comes to rest before the 1 kilogram because the one is lighter and starts with more speed. So watch, when the blue stops, or excuse me, when the red stops moving, his friction turns off. It's going to happen right now. So the red's friction turns off, but the blue's friction is still turned on. So when the red comes to rest and his leftward friction turns off, the rightward friction on the blue is still turned on for a while, and that rightward force takes away the leftward motion of the center of mass. So we start with a net leftward force, so we gain leftward center mass motion. We end with net rightward force. We lose our leftward center of mass motion. Why? Because the leftward friction on the red is better when it's turned on, leftward net force. Then the leftward friction on the red turns off, but the rightward friction on the blue is still turned on. Rightward force takes away leftward motion. Did you get all that? Because that was a delicious paragraph length response, but I think the exam is in the can right now. So it's too late for them to add it to this year's exam. Maybe in the future though. Okay, so after the 2 kilograms comes to rest, the net force on the system is to the right. So the center of mass with a rightward force is going to lose its leftward velocity. Rightward force takes away leftward velocity. Okay, here's another couple of center mass questions I'm going to give you a couple minutes on. So we have an object, it's launched into the air over level ground, and the center mass is going to follow a certain parabolic path. At the very top, so you're going to see the animation, but you have to tell me what's going to happen before you get to see the animation. At the very top, the object is going to blow up into 4 pieces. The question is, and be very specific, when does the center of mass quit following the parabolic path? You're not going to give me a number for the time. You're going to say, oh, the center mass is going to quit following the parabolic path the moment the explosion happens. Or is it a different later time, right? Be very specific, but you're going to get 2 minutes to think it over on your, on your mark, get set, go. That's the end of that. Okay, so here's the animation. Did you write about this? So you'll see that the center mass is being traced by the white dots as the four object system explodes. The center mass still follows the parabola. And then this happens. Oh my gosh. When does the center mass stop following that parabola and start a new parabola? If you got when the first time any of the objects hits the ground, then you're right. The center mass stops following the parabola the first time one piece of the object bounces off the ground. Why? Because the center mass is in free fall only if the only external force is gravity. So even after the explosion, that's an internal force. That's an internal force, the explosion. So the only external force is still gravity. The center mass still follows that parabola until any other external force acts on any object in the system. So as long as the center mass in free fall and only gravity is acting on any of the objects, the center mass follows the same parabola. But if any other force, like the normal force from the ground, acts on any object in the system, then the center mass changes path. So you'll notice that the center mass changes its path again. Every time one of the objects touches the ground, the center mass changes to a new parabola, right? Okay, all good. All right, if you'll look at this animation right here, you'll see a blue ball that's being shot up from the ground and a red ball that's being dropped from rest. So what happens is that at the same time the blue ball is shot up and the red ball is dropped from rest, then they're going to collide and stick, and they're going to rise up to the blue's initial point. I give you some times to help you out. So I say at time equals 0, the blue ball is shot and the red ball is dropped. At time equals 1 is the collision, and time equals 2 is when they rise back up to the red ball's initial position. So you're going to get 2 minutes for this. You're going to sketch a graph of the two velocities as a function of time, the red velocity and the blue velocity. It's a sketch, right? So do that on the same axis. So you're going to have velocity, time, a sketch for red and blue, velocity versus time on the same axis, up is positive. Then a separate v and t for the center mass's velocity as a function of time, where up is positive. Here's a bonus. Bonus is draw, don't sketch. Sketch means just give me the shape. Draw means put actual legit numbers on the axes. Let's see if you can do it, but you're not going to get much time to do it. It's only going to be a couple of minutes. On your mark, get set, go. That's that. So here's the animation, but with the graphs. And so you'll see the blue velocity and the red velocity as a function of time, where each of the vertical divisions are 10 meters per second and the horizontal divisions are half a second. So Here's what I'm going to say. In my mind, I'm going to say that the red velocity starts at 0, and in the first second, it's going to drop 10 meters per second because that's what gravity does. So look right here. We start with 0 velocity for the red, and it's going to drop 10 meters per second in the first second. Now, why is the red velocity going to switch from negative to positive 10? Because at the end of time equals 2 seconds, everybody's at rest. So I'm actually kind of drawing the red graph at both ends and coming back to the middle, right? So we end with 0 velocity and a free fall for a second before that. We start with 0 velocity and a free fall for a second before that. And then the velocity suddenly changes during the collision. Now, how am I building the blue graph? Well, the blue and the red graph are the same for the second, right, from 1 to 2, because the objects are stuck together. So because the objects are stuck together, then they both have the same velocity for 1 to 2 seconds, right? Now, here's what I'm thinking. How do I build the rest of blue's graph? Well, if red gained, look at what I'm pointing to. If red gained 20 meters per second, then blue, being the same mass, must have lost 20 meters per second during the collision. So I built red's graph first, working in from both ends. Then I'm going to build blue's graph by saying if red gains 20, then blue loses 20. So I'm going to make blue have a drop of 20 meters per second here. And then before that, you're in free fall. So what does free fall mean? Lose 10 meters per second every second. So this would be negative 10 meters per second, 0, 10, 20, 30, 40. So blue actually went from 40 to 30 meters per second, then dropped to 10 during the collision, and then to 0 when they stick together. But of course, so this is, I'll say that there. Okay, so I'll let you see that on the rewatch, right? You can pause the screen. If you're rewatching it, you can read through everything I just said. Okay, here's the center of mass right here. The center of mass was in free fall the whole time. There were no external forces. I know the two objects hit each other, but there are no external forces except when the two objects, except for gravity. So that means that the center of mass was in free fall the whole time. So here's what I'm thinking. If the only force is gravity that's external, then the center mass has to be in free fall, and that means its graph of velocity is a straight line with no kinks in it, negative 10 slope the entire time. Negative 10 slope the entire time. Now, I know the center of mass is at rest at 2 seconds because everybody's at rest at 2 seconds. So then I start there at the end with 2 seconds, and I work backward, making a graph whose slope is negative 10 meters per second every second. So that's how I constructed the velocity graph of the center mass. I just know that the center mass is 0 at time 2. I know that the graph is one of a free falling object with no external forces or jumps. So I just made a graph whose slope was negative 10 for 2 seconds, ending at 0. So we started at 20 meters per second. Okay, this is the part where the P1 kids can probably tune out. We have about maybe less than 10 minutes left to go. But you probably learned this if you're a Physics C student. It's on the formula chart. If you want to find the exact position of the center mass of 3 or more objects that are distinct objects, we call that discrete objects, then all you do is you do the following quotient. In the numerator, you add up every mass times his location, and then you divide that whole sum by the total mass. So if you do that for the x, sum of all m's times x's, divide by the total mass, you get the x of the center mass. Sum of all the m's times the y, their y's, divide by the total mass, you get the y of the center mass. And the m total is just the sum of each individual mass. So what you do is you take each individual mass times its position, get that sum, then divide by the total mass, and you know where the center mass is. So you're going to practice this idea right now of taking each individual mass, multiplying by its position, taking that whole sum and dividing by the total mass in order to find where the mass is located, the center mass is located of this system. So we have 2 more little 2-minute practices. Here's the first of the 2. On your mark, get set, go. This is just a quick crank it out calculation right here. So here's how you do it. The total mass is 3 plus 2 plus 1 plus 4. That's 10 kilograms. So now I'm going to take each mass and multiply it by its position. So up here I've got negative 30, and then I've got negative 4, because 2 times negative 2 position. 1 times 4 is positive 4, and then 4 times 10 is 40. So I get a grand total of m's times x's is 10. So the center mass position is the sum of all m's times x's. I get 10 over the total mass of 10. So it's at this position right here, 1 meter. Here's a little challenge. Do this problem again, but make this x equals 0, x equals 10, and x equals 20, and find out where the center of mass is. It's a different number, but it won't be a different place. Yeah, that's kind of nifty, isn't it? Last little bit here. We'll probably finish before 50 after the hour. So suppose instead you're given a single object, but its density is different in different places. Kind of trying to show that off here with the black and the white and how it kind of fades, like the density is changing of blackness or whiteness or whatever you want to say. Let's let lambda be the rod's linear density. And so that would mean that it's measured in kilograms per meter, not kilograms per volume like a volume density is. We call this a linear density. So what if you want to find the center mass of this? Well, what you do is instead of summing up each mass times its position, you integrate x times the density dx. So that means the more density that there is, the more the center mass is weighted in that direction. If there's more density on the left, then there will be, the x will be shifted to the left. If there's more density on the right, the density will be shifted to the right over m total. Well, how do you get the total mass? Well, that's a slightly different integral. The total mass is just the integral of the density dx. The center mass is the integral of x times the density dx over the total mass. So I'm going to give you one final problem here. This problem does not require you to actually do calculus. Instead, it's going to ask you to talk about what calculus you would do and then to reason in terms of calculus, but without actually doing any real calculus, which I think is what this exam is going to be like for the Physics C students. Are you ready? Here we go. You're given 4 rods. All of them are 4 meters long. Here are the different density functions for each one. Rod W, X, Y, Z have these density functions. Notice that the last one, that's the square root of X. So, and they're all 4 meters long. All 4 rods have the same total mass. I'm not asking you to prove it. I'm just asking you, how could you show that? And B, without doing any real calculus, rank them based on where their center mass is located from the left, okay? So where is their center mass located from the left? Now, I would encourage you not to do any real calculus, but man, it's easy to explain this ranking if you just sketch each of these functions. Sketch, not draw. Okay, here's some time. On your mark, get set, go. let's wrap this up. Okay, so again, I didn't ask you to actually find the total mass. How could a student show they all had the same mass? And all you had to say is integrate each lambda with respect to x from 0 to 4. Make sure if you talk about taking an integral, you're very clear about what the limits are. Make sure you say that. In case you care, they all integrate to 64 kilograms, okay? And so you just compare and make sure they all come out to the same amount, right? Now, here's part B. Rank the rods based on the location of the center mass. Look what I did. I sketched each of the density functions. I didn't draw them, I just sketched them. And so I'm going to say this. I'm going to say that X has the most leftward center mass, Y has the most rightward center mass, and W is farther to the right than Z is. Here's my thinking. X has more density on the left end than anybody else. Look at all this mass and density that's on the left that the other objects don't have. Then next, Z has some, not as much of his share of mass is on the left as X is, but some is because of the way the square root function bends. Then W has less mass on its left end, and Y has the least mass because of the way the parabola shoots up, right? So again, I didn't actually have to integrate any of this. If you want to, you can, but you should find that X, if the length is 4, then X's center mass is at 2, and then I think Z's is at 2.4, W's at 2.6 repeating, and Y's is actually at 3 if you actually want to go back and practice your calculus on this. Okay, so every object or system has a special point called the center of mass. The velocity of the center mass is total momentum over total mass. The center mass's motion can only change if there's an unbalanced external force on the system. And here's your equation for the center mass location from individual objects and from a continuous object that has density. I'm sorry, there's really no practice problems for this one. Center mass usually shows up in the form of a multiple choice question. They may ask about it on the P1 exam. If they ask about it on the C exam, that's very unlikely, but it's an important concept. So I hope that you got something out of it for sitting with me today. Please don't forget to find my Facebook page and look for the practice problems there. Either you're going to, I don't know, like, follow, bookmark, whatever, but you'll find them every day, and I'll see you next time.